particular lesson, we're going to discuss a little bit about Bayes' theorem. And Bayes' theorem can be super helpful. However, it can also be a little bit complicated in the way we have it set up. So I'm going to show you how to use Bayes' theorem, but I'm also going to show you a table method because I feel like the table method is a lot more intuitive and makes more sense with things that you've probably seen and witnessed in the past. So I'm going to show you both methods, and then you can decide which method you like the most and would prefer to utilize. So suppose a certain disease has an incident rate of 0.1%. That is, it afflicts 0.1% of the total population. A test has been devised to detect this disease. The test does not produce false negatives. That means that anyone who has the disease will for sure test positive for it 100% of the time. But the false positive rate is 5%. That tells us that 5% of people who take the test will test positive even though they do not have the disease. Suppose a randomly selected person takes the test and then tests positive. What is the probability that this person actually has the disease? So let's take a look at, there's a lot of different pieces of information that we have here. So I'm going to assume, well, we'll do this first. We will do the theorem first, and then we will do the table, and then see how they relate together. So when I'm looking at the first sentence, it says, suppose 0.1% has an incident rate. So that tells us that the people who have the disease is 0.001, right? Because we turn our percents into decimals. That means that a person who does not have the disease are at 0.99, so 99.9% of people do not have the disease since 0.1% do. And then let's talk about the testing. So we're going to be testing given that they do or do not have the disease in the next lines. So a test has been devised to detect this disease. This test does not produce false negatives. So this first line, this part here, the test does not produce false negatives. So anyone who has the disease will test positive. This is the probability that they test positive given that they have the disease itself is 100% of the time. However, this next couple lines, the probability that it tests positive given that there is no disease, so a false negative, is 5%, or 0.5%, excuse me. I need too many zeros here, 5%, so 0.05. So let's talk about Bayes' theorem, which is here. We are looking for a randomly selected person takes the test and tests positive. What is the probability they actually have the disease? So we're looking for the probability that they actually have the disease given that they tested positive. Now, the disease is going to be our A, and testing positive is going to be B, which will help us utilize the formula above. So it says the probability of A, so we need the probability of the disease times the probability of testing positive given that we have the disease all over the same sequence. So the probability of A, so the probability of having the disease times the probability of testing positive given that we have the disease, plus, now notice it has the not A in both here. So that's going to be the positive of having no disease or not having the disease times the probability of testing positive given that we have no disease. So looking for these probabilities, we found most of them up above. So the probability of having the disease here, we said was 0.001. The probability of having the testing positive, given that we have the disease, was whole because it had does not produce false negatives. All over the same 0.001 times 1 plus the not portion. So the probability of not having the disease, we talked about that up here. So the probability of not having the disease is 0.999. And then the probability of testing positive, given that we do not have the disease, we found that in one of our sentences as 0.05. So this will give us approximately 0.0196. So the probability that a person actually has the disease, given that they have a positive test, is approximately 1%, so about 1.96%. Now let's take a look at the table and see if we can make sense of this a little bit more. So let's assume that we're going to test 10,000 people. I'm choosing a large number because large numbers are better with fractions with respect to division and getting a more accurate decimal. So the larger the number, the better chance you are of getting as close as possible. You could certainly do 1,000 or 100,000 if you desire. In all of our examples, we're just going to use 10,000. That seems to be a good basis for a numbering system. So what do we know then? What do we know? So we know that a person has an incident rate of testing for to have the disease. So of all the people to have the disease is 0.0 or 0.1%. So 0.001 times 10,000 is 10. We also know that if they do not have the disease, of all of the people is 0.999 or 9,999, which you could easily have done by adding these two values or subtracting 10 to get 9,990. We also know that a person who, given the disease, so in this category, given the disease, and they test positive is 100%. So 100% of those who are testing, who have the disease would give us 10. So this category is 10. That means this row would have to be, it would be 0 for negative test because 10 plus 0 would still have to be 10 to make the total category appropriate. I also know that those who test positive, given that they do not have the disease, is 5%. So in this category, I'm going to take 0.05 times 9,990. And I'm going to get a decimal, but I'm just going to round it to 500. That means that my positive test category is 510. I don't know any other decimals, although I could certainly determine what they are, but I do have enough information to fill my table because I know that 510 plus here has to give me 10,000. So this column has to be, this cell has to be 9,490, and then this would also have to be the same value in order to make the column true as well. Right, now let's look again. So what it's asking for. So given the person takes the test and tests positive. So of those who are testing positive, what is the probability that they actually have the disease? So they actually have the disease is 10 out of a total of 510 who actually test positive. So again, if we look at the probability that we're looking for, disease, given that they test positive. Well, this means that they have the disease, given that they test positive. So given that they test positive was 510 people, they have the disease is 10, and when we plug that into our calculator, we also get the exact same decimal. I really enjoy the table. We'll see another couple of examples of this. So as we build it, it becomes a little nicer. So we're going to start on the next page with the table first, and then we'll build using Bayes' theorem to get there. Again, I'm going to assume 10,000 people, but a certain disease has an incident rate of 2%. If the false negative rate is 10% and the false positive rate is 1%, compute the probability that a person who tests positive actually has the disease. So I'm going to assume 10,000 people again. A certain has an incident rate of 2%. Well, 2% then of all people are going to have the disease. So 2% of 10,000 people gives me 200. That means to fill the rest of this column, that those who do not have the disease then would be 98% of 10,000, or subtracting, of course, gives us 9,800. So this gave us those who have the disease. If the false negative is 10%, so a false negative is they have the disease given that they tested negative, is 10%. So this category is 10% of those who have the disease will test negative, so 20 of them, which means those who test positive that they have the disease would be 180, since 180 plus 20 gives me 200. And false positive rate, this is the probability that they are positive given that they have no disease, is 1%. So under the positive test category, they do not have the disease. And of course, the total in this column is 9,800. So 98. Now we can find the totals by taking 180 plus 98 to get 278. I can find this column here by taking 10,000 minus 278, and I get 9,722. And then of course I know the negative column they have to add together, so this must be 9,702. We're looking for the probability that a person who tests positive actually has the disease. So we're looking for they actually have the disease given that they had a positive test. So given that they have a positive test, they have the disease. So putting it into English language, they have the disease given that they have a positive test. So of all those who have a positive test, there are only 180 that actually have the disease, or 0.647, or about 65% of people who have the disease given that they tested positive. Now let's look at Bayes' theorem and put that portion together. So we have the probability. It's the same one we just had. This is our A, this is our B. So the probability that we have the disease times the probability that we test positive given we have the disease over the same pieces plus the probability of no disease times the probability of testing positive given that we have no disease. Okay. So looking at our probabilities, we already know that the probability of getting the disease is 2%, which was at the very beginning. So 0.02. The probability of having the disease or having a positive test given a disease is 90%, since 10% was a negative test and we have a positive test. So this would be 0.90 times 200. Right, so we were given the opposite one. So given the information that we have to deduce other probabilities from that. And then we repeat this. So then the probability of not having a disease we found here. So the probability of having the disease was 2%. Therefore, the probability of not having the disease is 98%. As we know, it has to total to 100%. And the probability of having a positive test given no disease was that false positive rate of 1%. Oops, too many zeros, excuse me. Which then gives us, when we multiply, notice how close these are coming to the values up above. And it gives us the exact same percentage. Again, you can utilize the table or the formula, whatever makes the most sense to you. So let's try a different circumstance and just use the table to work our way through. A company has found 80% of its new management hires are meeting expectations while 20% are not. So to build this table, we're either going to be meeting expectations or we're not. And then they're talking about having sales experience. So then we're also going to have sales experience or not have any sales experience. What is the probability that a new hire with sales experience will meet expectations? So we're comparing sales experience and meeting expectations. Let's assume that we have 10,000 new hires. And then we'll fill in the table. So a company has found that 80% of the new hires are meeting expectations. So on the meeting expectations row, 80% of the new hires, which we said were 10,000. You could do 1,000 or smaller values if desired. But to keep things consistent, I'm just using 10,000. That means that 20% are not meeting expectations, which makes sense because you either are going to meet expectations or you're not. So therefore, 2,000 goes in this column. So of those satisfactory, so of those who are meeting expectations, 75% of them had sales experience. So 75% of those who met the expectations have sales experience. This, in fact, then would be 6,000. Also tells us then that 25% of the 8,000, because we know the row has to be 100%, would give me 2,000. But also 6,000 and 2,000 is 8,000, so you wouldn't necessarily need that decimal there, but just to showcase the different values. Now we're looking at while the unsatisfactory hires, 55% had sales experience. Now we're going to the unsatisfactory, 55% had sales experience. So 0.55 of those who were unsatisfactory. So I'm going to round a little bit here. So 1,100. And then, of course, then 45% unsatisfactory, did not have any sales experience too. So kind of putting all those portions together, or 2,000 minus 1,100 is 900. Now we can add the columns together. So 6,000 plus 1,100. So there were a total of the assumed 10,000 new hires, 7,100 had sales experience, while 2,900 of those did not have any sales experience. So let's actually do the probability. What is the probability that a new hire with sales experience will meet the expectations? So our probability is when they meet expectations, given that they had sales experience. So given that they had sales experience, did they meet the expectations? And this will give us approximately 0.845, or about 84.5% of new hires with sales experience will meet expectations. Now, just because the past three examples all had grabbed the numbers from the same columns does not mean that is how it's always going to be. So be careful with what it's asking. Certainly utilize the table version or the formula, whichever you connect with the most and are easily visible to see. I will not test you and force you to do one way or another.